In this section, we're going to work on continuing with our global optimization stuff, but in slightly different applications. So we saw some applications already. There were formulas given, but they were tricky because they had multiple variables. Here, we're kind of reversing that. I'm not giving you a formula, but generally there aren't multiple variables. So this is optimization problems, applied optimization. So I'm just going to crunch through, I don't know, a long list of examples here to try and give you some ideas. A lot of the formulas and things you use are going to kind of be reminiscent of related rates, or depending on who you took pre-calc from, you might have done parts of this already in pre-calc. We just couldn't do the calculus part. Okay, so I really like this one. There's this kind of barn fence problem that's really typical. You're trying to fence some rectangular thing and you're trying to get the biggest possible area. So this is a little bit of a twist, and I try and put some of the twisty ones on examples. So hopefully your homework ones are a little less tricky, but this one's not too bad actually. So we're trying to build this corral, shaded area, inside the bend of a river. So here's this 135-degree angle, and we really only need to fence from A to B to C. We don't need to fence the river sides. So bounded on two sides by the river and two sides by a mountain. Okay, so one thing is, to do this, we only get 1 mile of fence. So we know that as one of our kind of important restrictions in the problem. Otherwise, we just make a monster big one. We're trying to find the dimensions of the corral largest area. Okay, so first thing, we can pick out one of our variables. It's really a freebie. Whatever it is we're trying to maximize or minimize, that's what we want one of our variables to represent, and that's what we want our function to be. So let's say A equals the area of the corral, there we go, and we can kind of start working our way up. We already have a picture, so if I didn't have a picture, I'd draw one, but we can start working our way up to how would we find the area for a corral, and hopefully along the way we'll decide what we want as a variable. I've actually got some here. Let's scratch out this ABC because I don't need those, and I don't confuse that A with that A. So in the picture I gave you, there's already an X and a Y label, so we could use one of those, or we could pick something else entirely different for our other variable. The idea generally is that other variable needs to represent whatever it is you get to control or decide in this situation. So since we were asked for dimensions, I'm thinking one of those is probably a good plan, or at least something related to one. Okay, so here's how I do this. If you can just go straight to writing a formula, do it. But usually people, if they're going to get stuck on one of these, get stuck on not even getting the equation set up. So anything you can do with this sort of hybrid, write it out in words and use some math notation, I think helps. So if I were looking at this and I wanted the area, I would split it up into a rectangle and a triangle. So here's my triangle, and here's this rectangle that I have. You can, if you have a trapezoid formula memorized, you could try and use that as well. I'm not actually sure how that works. I think it should work fine. But this is what I would do. So I would say, okay, the area of the corral is going to be the area of this triangle that I have, plus the area of this rectangle that I have. And again, this is just your work. It doesn't have to be pretty. It's just to help you get started. So this is my structure. I know it's going to be the sum of two pieces, and they're both area pieces. And I can do even a little better than that. Area of a triangle is going to be 1/2 base times height. And the area of a rectangle is going to be its length times its width. You can use letters here, B, H, L, W. What I found is that people get really tangled in too many variables floating around, especially if you accidentally use a B here and a B over here and they're different. So I just use words until I picked a variable and I'm going to stick with it. Okay, so looking at this one, I think I'm just going to go ahead and use this as my variable. So what I'd really like to end up with is A is a function of X. If you temporarily want to use the Y, you can, but at some point you'll have to get rid of it. So just be aware of that. You pick a variable and you only get that one. Okay, so the triangle, base times height. Okay, so for one thing, if we're calling this height, this is an X as well. It's a rectangle, so that goes straight across. So I'm going to get 1/2 of X. That's height, but that's okay. And then the base. Okay, so here's where the 135-degree angle comes into play. If we break that up, there's a 90 here, which which means this is actually a 45, or you could get it because we're told that this was a 45-degree bend, so this is 45 and this has to be as well. Either way, a very small amount of trig tells us that if this is a 45, then this is also a 45, and that means that if our height is x, our base is also x. So we have a 1/2 x times x for the triangle, and then y times x for the rectangle. But again, if you use that y temporarily, it's fine. You have to get rid of it before you're done. This is a of x. Okay, so let's think about the getting rid of it part. Here's how to figure out how to get rid of it. If you look at that rectangle and you say, okay, let's say I picked an x value. What, if anything, is stopping me from just choosing whatever I want for my y value? And if the answer is nothing is stopping you, then we're in trouble. We probably can't eliminate it. But here, it's not true. We can't just choose any xy pair we want. The thing that's stopping us is that we only have 1 mile of fence. So if you can spot that thing that's restricting your choice, you can try to write that restriction up symbolically. So what I would say is that x plus y, well, you know what? I think in that original picture, y was actually supposed to be this whole thing, which means this is really y minus x. So if we're going to go back over to here, I think I lied to you a little bit just looking at the picture. So you could just name the bottom of that y. It doesn't really matter, but since it was already named, I'm going to stick with it. Okay, so then actually it makes this part a little easier. X plus y has to be 1. We only have 1 mile of fence to get around those two, which means y is always going to be 1 minus x. So whatever x is, we need to subtract that from 1 to figure out what's left for y. So over here, I have a 1/2 x squared plus 1 minus x, so it ends up being 1 minus 2x times x, which is a 1/2 x squared plus an x minus a 2x squared. Simplifying here, what we're going to do is take a derivative, so any simplification that seems to make that easier I think is worthwhile. So I'm almost done, but I would say I can combine here. If I have 1/2 minus 2x squared, that's negative 1/2, negative 3/2 x squared. Okay, so there's my function. That's generally the hard part. Sometimes there's some algebra mess, but it's not usually too bad. So we have a function that we input x, it outputs area. We want to maximize area. We want the largest possible area. So to do that, we need to think about endpoints and critical values, right? So let's work on critical values real quick. This is a nice easy one to take the derivative of, 1 minus 3x, which is going to equal 0 if x is equal to 1/3. So we need to check a of 1/3 for sure. The endpoints part can be a little bit tricky. So in this problem, we're looking for the biggest and smallest values of x that make sense. We do have the application, so that's going to restrict this a little bit. So for smallest possible x value, I would say it's 0. That's a terrible choice, but it is the extreme. If x is 0, then y just stretches out 1 mile down the river and we don't get any area at all, but that's okay. On the other end, I actually think it's a little trickier because as y shrinks, x is getting bigger, but y can't get to 0 because once we hit this corner here, we're stuck. There's nothing that says we can move this corner past this corner. That's kind of the end point. So it's actually, that one's cut off when this side of the rectangle mushes in and touches this corner right here, and then there is no rectangle, it's just a big triangle, which means this is 1/2 and this is 1/2, so x equals 1/2. So basically what we do for the endpoints is we find them ourselves. We look for a reasonable domain, which in this case is 0 to 1/2 mile of fence for the side x. And then we're just plugging them back into our function, which right there is the simplest version. So when x is 0, the area is 0. When x is 1/2, we get 1/2 minus 3/2 times 1/4, 3/8. So 4/8 minus 3/8 is 1/8. And then when x is 1/3, we get 1/3 minus 3/2 times 1/9. 1/9 is 1/6. So there's our check. Okay, so we found a critical value. We're really hoping that this is our answer, that x has to be 1/3 of a mile, but you have to check. So this is really important. I will every single time dedicate points specifically for seeing that you remembered to check that it really was the max. And here it is, 1/6 is bigger than 1/8, so it is in fact a max. And the last thing you should do is just go back and make sure you really answered the question. So the question was find the dimensions. I have one of them, x is 1/3 of the mile, but I think I should write down y as well. Remember that x and y have to add up to 1, so y just has to be 2/3.